There it is. This is going to be the last one for limits. We're going to take care of some notation, talk about some higher derivatives. Just so we can all be speaking the same language as we go ahead. Maybe talk about the idea of acceleration, velocity, and position as well. There won't be too many problems to do in this, and mostly just examples and showing you how we do stuff. So I'm not going to get too in-depth about anything. I'm going to leave this up to you to go through it. All right, let us see. So notation-wise, when we write something like this, f prime of x, that's meaning our derivative of the function. So f of x, we could say, let me write this in a little different, is the function. And this is the derivative of the function f. Yeah, no big deal. F of x. Well, we could also write something like this. Maybe we have this y is equal to 3x squared minus 7. Now let's introduce a little bit of new notation to it. It's the same idea, but we could say the derivative of y with respect to x, we could call it y prime. And I'll just let you know that the answer is 6x. Now that was what its derivative would end up being. But there's another piece of notation. It's saying the same thing. So instead of using f's, right, if we would have had f of x is equal to 3x squared minus 7, we would say that our f prime was equal to 6x. And I'm not explaining the quick jump. Maybe you know the power rule. That's fine. We'll do that in chapter 3. We'll start using it. For now, we need to show our steps. So there's just a new piece of notation. So instead of you just throw a little prime on something, saying that you've taken a derivative on it. And we'll start learning that we can take a derivative on top of a derivative on top of a derivative. We can keep taking derivatives all day long if we need to on some functions. We just keep going. Okay. So maybe we have this. F of x is equal to sine of 3x. And I'm not explaining, I'm not trying to tell you how to find the derivatives of these things. We could say that it's derivative, and I just do a bunch of fancy footwork, and I find out that this derivative is equal to 3 times cosine of 3x. I'm not explaining, there's no reason for you to know what this is unless you know how to do the chain rule and a bunch of other stuff. It just is. That's just truth. Now, we could also write it as this way. Y is equal to sine of 3x. And we could write down that y prime. Right? So we're writing the same thing. We're just calling the function something different. We can go y prime is equal to 3 times cosine of 3x. Also, y isn't under the same restrictions as f of x. F of x needs to pass the vertical line test. Y doesn't need to pass shit. So maybe there will be times when you want to use just x's and y's and not f of x's. But we could even take this a step further. Now the notation we're using up here it's kind of known as like Newtonian, or like from Newton. By throwing a little apostrophe on it. And soon we'll be putting quotes on it. And we'll put 2 of them for a second derivative, and then 3 of them for a third derivative, and shit like that. But Newton wasn't the only one that was coming up with calculus back in the day. Gottfried Leibniz, the German man, well he was also coming up with this at the same time. He actually, I think, published beforehand. So if you were to go to Germany, you were to ask who's the father of calculus, and they're going to say Gottfried Leibniz. They're not going to say Newton. We're going to say Newton because we're allied with England, right? Newton's from England. And actually the stories say Newton did come up with it sooner. He just didn't publish in time. But whatever, there's another different notation. And this is called Leibniz notation. Let's go with this. And we have it as Leibniz. And Gottfried Leibniz, was born in 1646, studied a little law, theology, philosophy, dabbled in some mathematics, came up with calculus, or one of the fathers of calculus. So we'd have a different notation. If we were to say y is equal to sine of 3x, and we're about to go write down its derivative, don't worry, nothing's changing. You don't look at the right-hand side. I'm just giving you an example. Now, instead of writing y prime, here it is. Here's the notation. dy over dx. These are differentiation operators because they just basically tell you what you're doing. It's the operation of differentiation. Don't stress about this shit. Don't stress. Like, it's a lot of freaking notation. For right now, just be like, dude, it's the same thing as f prime. It's the derivative. It's just this picture. But what it's saying is it's the derivative on y with respect to these x values. So it's telling you what to take a derivative on. It's saying the variable is x that we're going to be taking a derivative on. The variable is x that we'd be taking that derivative on. That's kind of what it's saying. Now, dy dx, again, I got to hit you with notation. I just got to do it. Dy dx is actually just equal to the, oh, wait a second. No, it's not. It's equal to the limit of this. The limit is our change in x goes to 0. Change in y over our change in x. Have you seen that notation, those little triangles, the deltas that mean the change in? Change in y over change in x usually means just the slope. But we're saying that our dy dx is just making it to where that derivative, oh, oops, I'm sorry. When the x's get super close together and you end up with a freaking 0 over 0 case. I mean, we've never talked about a 0 over 0 case, huh? But that's what's happening. So it's just a notational thing. Just take it for what it is. It's just notation. All right. Now let's talk about this. So I'm going to give you an example of something. So f of x is equal to, let's go 8x cubed plus 3x minus 1. Now I'm going to go through this, and I'm just going to start taking a derivative. And then I'm going to take another derivative on that, and then another one on that, and then another one on that. And then I'm just going to keep going. So I'm not explaining how it gets to here. I'm using tricks. I've learned the tricks. And the derivative is 24x squared plus 3. And you might be able to just look at what I'm doing and see that, like, oh, there's a fast way through this. And then if we were to take another derivative, here's the notation for it. We would write f of and the x, but since we're taking a second derivative, we would just write it twice. Now, we're taking a derivative not on the original function, but now on our derivative. It's taking a derivative of a derivative. And then it just turns out that it's just 48x ends up being that derivative. Now we can take another derivative on top of that, and here comes the notation. We would write f of with the x, but now we're not going to write 3 of them, or 2 of them, we'll write 3 of them. That's saying the third derivative, and it just happens to be 48. Now we can keep playing this game forever. We can just keep going. Well, at least with this game. So I'm going to go to the next derivative, and now we go to like Roman numerals. You can do that to the fourth, and we can say that actually the answer is 0 there. Or there's another way that this could be written. It depends on who's writing it. We can also, the numbers go up. You don't know all your Roman numerals. What you do is you just put a parenthesis around it. And that's saying the fourth derivative of x. And it just happens that answer is 0. And then we could write the fifth derivative of x, and that's also going to be equal to 0, which we could have written this way as well. Because if you're getting up to the like, hey, we're going to write down write me down the 51st or the 59th derivative. I don't know my freaking Roman numerals very well, so I'd be like, let's do it this way. And say that's the answer. So that notation is just telling us which derivative we're on. So we started with our f of x, we worked our way down. Now I'm going to show you in Leibniz, just hold on, do your best. Writing the same thing. All of our answers are going to be the same, but I just got to show you how it's going to be. So that would be the derivative on y with respect to x is equal to, we get our 24x squared plus 3. Now for us to take a second derivative, now this is where the notation gets really jacked up. We're going to put it in as, now here it goes. Since it's the second derivative, we're going to put the square on the d and the square on the x. Don't ask me. Just for right now, just take it. Just let it go. Just let it go for now. We'll be back to this stuff. You got enough on your plate. Fourth derivative. We're coming in hot like this. That's supposed to be a y. And we get our 0. That's just Leibniz notation. Don't worry about it. Don't trip about this yet. I'm not going to test you on it until afterwards. You'll need to know what that notation means by exam 2. But I wanted to introduce this. Now, the last piece I wanted to tie together is the fact that, hey, if you start off with your position function, the position, and you take a derivative on your position function, you're going to get the velocity function. And if you take a derivative, a second derivative, 2 of those derivatives on the position function, which is actually just the derivative of the velocity function, oh my gosh, the frickin' world is amazing how it works like this. This is actually just the acceleration function. So everything is all tied together. Shit, if you were to actually go, I'm just putting this one in for fun, triple prime, which would be equal to the second derivative of velocity, which would be equal to the derivative of acceleration, which is actually just equal to what we call the jerk function. Think about getting jerked in your seat. Jerk function. I would usually give you an example in class of what it is, but it's no big deal. But hey, you take derivatives on the change the position with respect to time is called velocity. Hey, think about how when your velocity changes. We're cruising along, and then we speed up. Isn't that called acceleration? Or deceleration? Go fast and hit the brakes and slow down. Isn't your velocity slowing down? It means you're decelerating. And if your acceleration changes, that's your jerk function. Fun shit. Good luck on your test. Hope you kick ass. Hope this has been helpful for you. Hope you don't hate my voice too much. Don't worry, by the end of the semester, you will certainly hate my voice and hate me. See you.